Hello guys, welcome to another video. So in this video we are going to study about definite integrals, and we are specifically going to look about some of the problems. So in the last one we did some problems and some pretty good ones actually. And in the last lecture the problems were somewhere around the box function and then the cosine integral, also related to the following property. So this property is integral of a to b f of a plus b minus x dx is equal to integral of a to b f of x dx. So this is the property that we used. We also used a property as follows. Two times 0 to a, and this happens only if the function is even. So I will write it down. So this when f is even, which means that f of x should be equal to f of minus x, and it is 0 when that is f of x is equals to minus of f of minus x. So we did these two problems. Now from today's lecture what we are going to do is we are going to solve a bunch of integrals, and we are going to see how they actually put the values in, and we're going to learn some new stuffs like we are going to use some of the infinite series. We're going to use some methods called Feynman tricks of infinite integration and stuff like that. So to start off, let us do this integral, which is actually a pretty hard one, and it won't be covered in your normal courses unless you are in college, but still it can be solved when you are in high school. So if you remember, I had talked about this before when starting the integration, that this integral equals pi by 2, and I haven't actually told you how to find that integral. And I told you that there is no indefinite integration for this function sine of x upon x, because that this is just not integrable. So to make things clear, to evaluate this integral we would need some kind of other method. So one of the known methods is complex analysis, which is basically calculus in the complex plane, but we are obviously not going to do that because that is way out of scope of the syllabus of whatever we are studying here. And another method which we can use is parametrization. So this is a method which we can use to solve our current integral. How does this work? Let us see. So we are basically defining a function f of a, and where a is a real number and a is greater than equal to 0, that is a is non-negative. The function looks like this. So this is the function, and this f of a, and obviously a is greater than equal to 0. This f of a thing, we actually do not know how to find it, or how does this help with our actual problem, right? Because as you can see, the integrand has rather become more complex than being a less bit complex, but I'll show you exactly how this would help us. So watch this, we can see that f of 0 is defined, and it is defined as 0 to infinity e to the power minus 0x sine of x by x dx equals to 0 to infinity sine of x by x dx. So f of 0, the function, is basically the desired integral which we are trying to find the value of, right? And also notice that this also holds, and why we can interchange the integration and the limit is something I would like to discuss later, but for now understand that this is possible. And what we see here is this expression right here. Now you know that a is non-negative, and we have eliminated the case for a equals to 0, and we are tending a to infinity here, and x is always positive. So right, this holds, and since this holds, what we can conclude is this equals to 0. So our two results are, firstly, f of 0 here is equals to the integral we are trying to find the value of, and limit a tends to infinity, f of a is basically equal to 0, and this is basically due to the uniform convergence of the integral, but that we shall discuss later. So this would anyways, this problem will be done in two parts, so we shall look forward to the next part where we shall prove some of the identities that I'm going to use. But for this part, let us focus on how to define the function f of a completely and how to make use of it. So recall again the function f a, because once we are done with the special values that we are finding, we need to work with the actual function, and we need to find some way to evaluate it. Because clearly, if I have defined a function which is not really matching to the actual integrand, but in some ways the value 0 gives you back the desired integral, so there is something that we can do with this function to get the value of the integral, right? So what we can do is we can differentiate both sides with respect to a. So it's very important that we are differentiating with respect to a, where a is a variable, and by Leibniz rule of differentiation under the integral sign, you would get something like this. And I would state Leibniz rule of differentiation here after I write this thing. So this basically becomes minus 0 to infinity e to the power minus x into sine of x by x dx. And Leibniz rule of differentiation basically says that so this is the Leibniz rule of differentiation under the integral sign. And the statement of the thing is, if then what happens is as follows. Suppose you have d dx and you have an integral, that is you're differentiating the integral with limits of ux to vx, and inside there is a function f of t dt. We do not yet know if f of t dt or the function f of t has something in relation to x. So it might be the case that f is a dual function or function of two variables, three variables, we do not know yet. But what it says is for as follows. So this is basically Leibniz rule of differentiation under the integral sign. So let me just read it out again and may make any doubts clear here. So if u of x and v of x are two functions of x which are differentiable, and if f is integrable and f is continuous at all values which u of x or v of x attains, then if you are trying to differentiate an integral with limits u of x and v of x, and the function you are trying to integrate is f of t, if you differentiate it with respect to x, the answer becomes v dashed x, which is the derivative of vx, multiplied by f of vx minus u dashed x into f of ux plus u of x into v u of x to v of x, the integral. So the limits remain same, but what you do is you differentiate the function f of t with respect to the variable which we were differentiating the original integral with. That is why this is called a dou sign. It's called dou x instead of ddx, because it's a partial differentiation sign. And in partial differentiation, we treat the function as just the function of the variable which we are differentiating with, and everything else remains constant. So if f of t had some, it's a, let's say it's a function of two variables t and x, then t would remain as a constant, or it would act as a constant here, right? And that is the only way, because when we had differentiated the integral in our result, what we did is dou a of e to the power minus ax sin x by x, and this resulted, because sin x by x is constant, as it does not contain anything of x, anything of a, the differentiation was simply of e to the power minus ax, where a is the variable, and this gave us sin x by x into the extra thing is minus x, which is the constant. The constant comes out and the variable remains, which gave us minus e to the power minus ax sin x. So this is how we did it. Now in the next video we shall continue this problem and we shall see how to evaluate this integral. Specifically there shouldn't be any x here, sorry, it's only 0 to infinity e to the power minus x sin x and a minus in the front, and that's the derivative of f dash t. We would be trying to evaluate this integral in the next one, and then we shall see how to proceed to the next one. So thank you for this video, and do check out the Breatter's math app in the description. It's a math app where you can find all the theory and video lessons. Thank you.